So in this question, the question is the length of the pendulum is L and the mass of the bob is M. It is suspended in a toy train. The toy train is moving in circular track of radius r with speed v. The pendulum makes small oscillations in a radial direction. About its equilibrium position, find the time period of the oscillation. So the problem is like this is, let's say, a circular track, and somewhere in the circular track we have a toy train that is moving, and the radius of the circular track is r. Now in this circular track, the so if the toy train is at rest, okay, when v is 0, in that case the bob, the simple pendulum, it will be lying vertically like this. It will be hanging vertically, but as soon as it establishes, the toy train starts moving and v is non-zero, then this pendulum, it will shift radially outward direction. So let's say this was a track, then it will move slightly to the outward direction, in this direction, and away from this vertical that was initial equilibrium position. So it will be like this, as you can see. Now this will be its new equilibrium position, and now the oscillations in the pendulum will take place about this new equilibrium position, as you can see in this figure, that now the phi naught was the new equilibrium position, and about this equilibrium position it is oscillating with this very small angle theta. We always have to remember that this is about very small, for very small angles. So let's first try to understand the condition of the new equilibrium. So here we have this m times g, that is the force because of the acceleration due to gravity acting vertically downward on this small bob, and this mv squared divided by r is the centrifugal force that we need to apply on the bob while it is moving in the toy train, so that the Newton's laws becomes applicable in this case. So if you see, the condition of new equilibrium will be this: we will try to equate the torque, because the net torque will be 0 in the equilibrium position. So this mg is the force that is acting. Now its component, as you can see, which will try to restore it, that will be mg times, it is the sine of phi, the angle between the vertical and the equilibrium position, new equilibrium position of the pendulum, and it will be, so basically here I don't need to consider this torque, I only need to talk about the force. So this mg sine phi naught will be equal to the radially outward direction force, this one. So if I take its component along the direction of around the negative direction of this mg sine phi naught, it will be lying in this direction. So, and this will be phi naught. So it will be mv squared times cosine of the phi naught divided by r. So this is the condition of new equilibrium. Now let's come to the part of oscillation. In the oscillation, here this bob is oscillating about this mean position. This is the mean position. It is oscillating with some angle, let's say theta. So now let's say at this position, this angle is phi naught plus theta about from the vertical. As you can see, these are parallel, so this will be phi naught plus theta. Now the restoring force that will be acting in this case will be mg times, so we again have to take the component of this force in the direction which tries to restore the motion. It try to bring it back, the bob towards its equilibrium position. That this will be mg times sine of phi naught plus theta, and this is equal, this is this restoring force, this is since this force is acting away from the center, so its component will try to reduce this restoring force. The component of this force will be diminished because of the effect of this centrifugal force component in this direction. So here it will be minus mv square upon r, and again we will write it like this. This will be phi naught plus theta, and the component of mb square upon r in this direction will be mb squared upon r times cosine of the angle. So it will be cosine of theta plus theta. This is the force, this is the restoring force that will try to bring this bob back to its mean position or the equilibrium position. Now this is the dead force. Now this force this is the net force acting, so this F will be mg sine phi naught plus theta minus mb squared upon r cosine phi naught plus theta. So this force will make a torque act on this bob. So this is the force, that is the net force that we have, that is acting in this direction, and it will try to bring it back by applying a torque, because it will apply torque about this point, and this is the length of this pendulum is given to be L. So we will determine the torque, and that will be F times L is equals to mg sine phi naught plus theta times L minus mv squared upon r cosine of phi naught plus theta. Now this is the torque. Now we know that torque is the moment of inertia times the angular acceleration. In our case, if we write here, this F times L is basically the torque. So this is I, that is m L square, which is the moment of inertia, and the angular acceleration, that is d2 theta upon dt2. Basically this is phi naught plus theta, but since phi naught is a constant and theta is the variable here, so we can simply write theta is equals to mg sine phi naught plus theta times L minus mv square upon r cosine of phi naught plus theta. Here what I have done, this I know that moment of inertia times the angular acceleration is the torque, as simple as that. So this I is the moment of inertia, which is ml square, that is the basic definition of moment of inertia, and alpha, that is the angular acceleration, it is like d2 theta upon dt2, that is the torque, and the torque in our case was F times L, and I have simply equated this, and I have my equation. This is my equation. Now in this equation, what I will do, I will bring all the coefficient of d2 theta times d2 theta upon dt2 to the right side, and I will be left with the following equation. Now what I will do, I will expand these formula, sine phi naught of theta and cosine of phi naught plus theta. So after expansion, this is what I got. Now what I will do, since these angles are very small, this theta part is theta angle is very small, so I can replace sine theta with 0 because theta is very small. It is almost equal to 0, and this cosine of theta, since theta is very small, so cosine theta will go to 1. So I can write it, since under this limit that theta goes to 0, so cosine of theta is 1, and under the limit theta tends to 0, sine of theta is 0. So when I substitute these in the above equation, I will get, so no, I will, since theta is very small, so when theta is very small, then sine theta goes to theta, it is approximately equals to theta, and when theta is very small, let's say it's going to 0, then cos theta can be taken to be 1. So these are the substitution that I make in the above equation, and I will get the following equation. And if I rearrange this equation, I will keep the coefficient of theta in as a single term and the rest as other single terms. Then I will get sine phi naught plus g upon L, minus b squared upon RL cos phi naught. This is one part, and the theta part will be g upon L cos phi naught plus b square upon RL sin phi naught theta. Now if this is our equation, now from in this equation, if we see, then the first term on the right hand side, this term, and if we look at the first equation, this was our first equation, then we can say, if we can slightly modify this further, then we can write, we remove m from the both the sides and we divide both the sides by L. Then I can write it like g upon L sin phi naught equals to v square upon RL cos of phi naught. And if I use this equation into the final equation, then I can very clearly see that the first term, it vanishes, this term will vanish, because this is exactly equal to what I have here, and that I got from the equilibrium condition. So my equation will become d2 theta upon dt2 is equals to, this will go to 0 and the first term on the right hand side will go to 0, and I will be left with the other term. From equation 1, if we see that this g upon L sin phi naught equals to v squared upon RL cos phi naught, so this gives us tan phi naught. If we will take the cosine of phi naught in the denominator of the left hand side and the coefficient of sin phi naught on the left hand side towards the right, then what we get it that tan phi naught is equals to v squared upon RL, and this is divided by g upon L, so we will be left with v square upon RG. So from equation 1 we get this. Now it can help us to determine the cosine of phi naught and sine of phi naught, and we will substitute them into this equation. Let's say this is our equation 2, and then we can simplify further. So this cosine of phi naught will be RG divided by v squared plus RG squared, so this will be 4, and sine phi naught will be v squared divided by v to the power 4 RG squared. Now we will substitute these two values, of course cosine of phi naught and sine of phi naught, into our equation 2, and then the result will be very much clear. So this is our equation that we have and we will further simplify it, and then we will compare it with the equation of the SHM, because this is what we are going to get. So this will be my final equation for this equation of the oscillation for this pendulum. But in this whole equation, what I have done committed a blunder, and the blunder is that while I was writing the equation of the motion of the oscillation for this bow, I did not use the negative sign in front of this. This should be a negative, because this is acting against the motion of the bow, against the oscillation of the bow. This force, this is the force, and the oscillations of the bow is in this direction, and the restoring force is in this direction. That's why I need to put a negative in front of the force on the right hand side. So everywhere I have to put a negative. So this, now in this equation, I know the equation for the SHM. It looks like something, this is equal to theta, and if I compare this equation with the equation of SHM, then I can write that this angular frequency that omega it represents, and omega is equals to plus Rg squared divided by RL, and I can, let's say, square this. This is what angular frequency will be in our case after comparing with this equation. Now for the time period, because we have to determine the time period, so time period is nothing but, this is t, the time period is 2 pi divided by omega. So I can write it, this will be upon v to the power 4 plus Rg squared. So if I write it in a slightly less complicated form, it will be 2 pi RL divided by square root of p to the power 4 plus Rg squared. So in this form, so I will bring this R in the denominator, so it will be R squared plus G squared, and this is the required expression for the time period of such in such condition of the bow.